Today we're going to be talking about how to determine whether two vectors are orthogonal, parallel, or neither. The first thing we want to keep in mind is that orthogonal essentially means perpendicular. Technically, they mean different things because we can't really call two vectors perpendicular necessarily, but it's still a 90-degree angle between the two vectors would be orthogonal vectors in the same way that a 90-degree angle between two lines would be perpendicular lines. So essentially, we're talking about the same thing in the sense that we're talking about a 90-degree angle between the two vectors, making those two vectors orthogonal. Parallel vectors are going to be the same as two parallel lines, and it doesn't matter which direction the vectors are going in, if they're going in the same direction or the opposite direction, they're still parallel to one another in the same way that two lines are parallel to each other. And then obviously if the vectors are anything besides parallel or orthogonal, then we say that it's neither parallel or orthogonal, and we'll give an answer of neither. So the first thing we want to do is check to see whether these vectors are orthogonal to one another. And the way that we do that is by finding the dot product of the vectors. Remember that the dot product has us multiply the components of the two vectors together and then add all of those products. So we say that our dot product of A and B is equal to, let's multiply our x components. So we say -5 times 6. Then we add to that the product of our y components, so 3 times -8. Then add to that the product of our z components, so 7 times 2 in this case. If we simplify this, you see that we get -30 minus 24 plus 14, which is going to be equal to -40. Since that does not equal 0, these vectors are not orthogonal. Only if the dot product is equal to 0 can we call the vectors orthogonal. So we know that they're not perpendicular, they're not orthogonal. Now, if the vectors are parallel, their components will be equal to one another, or their factored components will be equal to one another. In other words, if we had two vectors, -5, 3, and 7, and -5, 3, and 7, they would be parallel. Or if we could factor something out, like for example this vector here, b, we can say that b is equal to, factor out a 2, we could say 2 times 3, -4, and 1. We can factor out a 2 and simplify that. If we got a factored version, this 3, -4, and 1, that was equal to this -5, 3, and 7 here, then we could say that the vectors were parallel. But that doesn't happen in this case. So in the example of A here, these vectors are neither orthogonal nor parallel, so we'll go ahead and say neither for this case. Now if we look at example B here, where we have A equals 4, 6, and B equals -3, 2. Let's try our dot product to see if they're orthogonal. So we'll say the dot product of A and B is going to be our x components, 4 times -3, added to the product of our y components, 6 and 2. When we do that, we get -12 plus 12. That is equal to 0. Therefore, our vectors are orthogonal. They can't be orthogonal and parallel at the same time, so there's no need to check to see whether they're parallel once we've determined that they are orthogonal with one another. So that's example B. If we look at example C here, we have a vector in slightly different form. We have components I, j, and k. We can change these vectors to be in the same components as examples A and B. We just take the coefficients on the I, j, and k components. So the coefficient on I here is -1. The coefficient on j is +2, and the coefficient on k is +5. So we say that A is this -1, 2, and 5. B, in the same way, is 3, 4, -1, like this. Let's check to see whether or not they are orthogonal. I can already tell by looking at them that they're not parallel because their components are unequal, and they can't be factored to get to the point where they are equal. So if I try the dot product of A and B, I'll get -1 times 3 plus 2 times 4 plus 5 times -1, and when I simplify, I get -3 plus 8 minus 5, which I can see is going to be equal to 0. Therefore, I know that these two vectors are orthogonal because the dot product is equal to 0. So I can conclude that. Now my last example here, I can convert in the same way that I did example C. I can say A is equal to, and taking the coefficients here, 2, 6, negative 4. And I can say that B is equal to negative 3, negative 9, and positive 6, like this. I can check to see whether or not they're orthogonal by taking the dot product. So dot product of A and B is going to be 2 times negative 3 plus 6 times negative 9 plus negative 4 times positive 6 is going to give me negative 6 minus 54 minus 24, and I can see already that that's going to be a very negative number, not equal to 0. So I know that they're not orthogonal. I just need to make sure that they're not parallel before I say that it's neither. Notice that out of A and B, I can factor a couple things here. So for A, I'm going to say A is equal to, here I'll factor out a 2. Factoring out a 2 gives me 1, 3, and negative 2, like this. For B, I can factor out a negative 3. So if I factor out a negative 3 here, I'll get 1, I'll get positive 3, and I'll get negative 2. And as you can see, I've gotten the same thing for my vector representation here, 1, 3, negative 2, and 1, 3, negative 2. It doesn't matter that I have this 2 and negative 3 pulled out in front. This tells me that my vectors are parallel. So I'm going to say my vectors here are parallel like this. So if you can get the two vector components to equal one another, then you know that your vectors are parallel. That's how you determine whether your vectors are orthogonal, parallel, or neither.